Good?
Yeah.
Right. So last time we introduced Diophantine approximation, so approximation of real numbers with rational numbers, and some interesting categories of real numbers. So epsilon Dirichlet improvable numbers, which are numbers alpha in R, for which, for all sufficiently large Q, big Q, this system has a solution. We also introduced singular numbers, which are the intersection of all Dirichlet improvable numbers, so that are Dirichlet improvable for all epsilon, so they correspond to this intersection here. And I also didn't introduce another set, which is called the set of Dirichlet improvable numbers, which is just the union of epsilon Dirichlet improvable numbers. Okay, and I also introduced badly approximable numbers, which are, well, essentially numbers for which a corollary of Dirichlet's theorem is the best one can do. So this inequality is true for all fractions p over q. Okay, and I have to rectify a mistake I made last time. So, so thanks. John, for asking the question. So, so singular numbers in R are only rationals. Okay, in reality, in higher dimension, one can prove that there are many more numbers. Okay, so it's not just the rationals, but in dimension 1, it's just rational numbers. On the other hand, Dirichlet improvable numbers, surprisingly, are rationals and badly approximable. So, in a way, these are numbers for which you can prove Dirichlet's theorem, and they include badly approximable numbers. Okay? Good. So this gives us a motivation to kind of dig into this dynamics on the unit tangent bundle, and somehow this, as an application of this of dynamics on this space that I have defined last time, we will be able to understand some of the properties of these sets. Okay, so, and I introduced the hyperbolic plane, the unit tangent bundle, which is essentially the set of couples ZV, where Z is an H and the length of V is equal to 1, the hyperbolic length. I also introduced an action of PSL to R on the unit tangent bundle, which is just so A, B, C, D dot ZV is just AZ plus B divided CZ plus D, and then you have the differential of G applied to V. Okay, and this one can do the computation, it's just CZ plus D squared V. Okay, so this is how the action is defined, and this action is simply transitive. So there is an identification between elements of PSL2R and elements in the unit tangent bundle through this formula. There's also a geodesic flow, so an action of R on the unit tangent bundle, which is essentially start from the point ZV and follow the unit geodesic. And we've seen that through this identification star, this flow can be interpreted as right multiplication by these matrices. Okay, so today I'm gonna take this dynamic and make it, in a sense, more interesting by folding up the unit tangent bundle. Okay, so let me give the following definition. So a Fuchsian group is a discrete subgroup gamma of PSL2R. Okay, so PSL2R has a topology because, in a way, one can see it as a manifold. Okay, so endowed with the structure of a real manifold, and so it has a topology. And the space that we are going to work with is G mod gamma, where G is PSL2R And gamma is just a Fuchsian group, but you can all think of gamma as PSL2Z, which is the group that we will be interested in. Okay, so this is, one can show that PSL2Z is a discrete subgroup. Good. And today's goal is to do two things. So number one is to introduce a metric which I'll call dx, okay? X is my space G mod gamma. Again, G mod gamma is, of course, just the set of classes, equivalence classes of the form gamma G, such that G is Ng. Gamma is not necessarily normal, okay? So this is just, it's just a set, okay? It's not necessarily a group. So introduce a metric dx on this space X, okay, and number two, introduce a measure. Okay, a measure, and also push down the geodesic flow. So when I say push down, I mean from G to G mod gamma. Okay, so these three ingredients will allow us to do ergodic theory. Okay, and by using the tools of ergodic theory, we can then get some information about those numbers. Okay, so let me start from the metric. Okay, so so one has the following result. So proposition: every closed linear group and you can think of G as PSL2R. Okay, so I will say what a closed linear group is in a moment. So admits a left invariant metric dg. Okay, so left invariant means that if you take two elements in G, so G1 and G2, and you consider the distance between G, G1 and G, G2, this is also equal to the distance between G1 and G2. For all G, G1 and G2 and G. Okay, so, and what is a closed linear group? This is just, say, in R, so let me write it like this, R2 by 2. Okay, so R2 by 2 is just the set of matrices with real coefficients, 2 by 2 matrices. Okay, this is just a closed subgroup of, say, SL2R. Sorry, GL2R. Okay, so this is just any group of matrices, and also you can do it in higher dimension. Okay, so and you can take matrices with d coefficients, with the d rows, d columns, and real coefficients, and consider a closed subgroup. And we call any such closed subgroup a closed linear group. Okay, so these closed linear groups in reality are the same as Lie groups. Okay, but this is a deep fact that I'm not going to prove here. Okay, so and yeah, so by knowing this, an idea of proof of this proposition is the following. So you have the tangent bundle of this closed linear group. So PSL2R, you can show, it's not immediately clear why PSL2R should be a closed linear group, because this is just a quotient of SL2R. SL2R is clearly a closed linear group, but whenever you quotient by plus or minus the identity, it's not immediately clear why you should obtain a closed linear group. But in reality, you can show that there is a good embedding of PSL2R into some higher dimensional matrix space. Okay, so 4 by 4 matrices, for example. And so you can see it as a closed linear group. Okay, so knowing that this is a closed linear group, as I think Davide showed us, one can identify the tangent bundle as G cross G, where this is the Lie algebra. Okay, and if you know that the unit tangent bundle looks like this, then essentially you can just take any metric. So take a fixed inner product on G on the Lie algebra, and then you can drag it around your group G. Okay, so this allows you to essentially define a Riemannian metric on G. So this gives a Riemannian metric on G, and therefore a distance. Okay, so by using by having a Riemannian metric, you can again define the distance as the length of the inf of the lengths of all curves that connect 2 points. Okay, so all good. You seem to be concerned. Okay, good. Right, but okay, I won't go into this. Like for you, it's enough to know that there exists a left invariant metric. So a metric on G with this property. Right, so if we have a metric on G with that property, then we can just push it down. Okay, let me erase this. So having dg on G equal PSL to R, we can define, so for any gamma contained in G discrete, okay, we can define the following metric. So again, I will denote by X the group G mod gamma. We can define dx gamma G1, gamma G2 as the minimum, sorry, not the minimum, but the inf, okay, which is also a minimum, for gamma and gamma of the distance between gamma G1 and gamma G2. Oh, sorry, I forgot dg here. Okay, so gamma 1, gamma 2 in gamma, dg gamma 1 G1, gamma 2 G2. Okay, but since the metric dg is invariant, this is also equal to the inf for gamma and gamma of the distance in G between G1 and gamma G2. Okay, because you can just take this gamma 1 and bring it to the other side. Good. Okay, so then what I want to prove now is the following thing. So with this metric, X equals to G mod gamma is locally isometric to G. Okay, so I also forgot to say something. So this left invariant metric that we have here, remark, this comes from the construction of the left invariant metric, so I don't want to prove this, but this left invariant metric induces, so dg induces the Euclidean topology. On G. Okay, so what happens is that you can see your group as a group of matrices, closed group of matrices. On a closed group of matrices, you have the topology induced by the group of the set of all I don't know 2 by 2 say matrices. Okay, and this gives you clearly an induced topology, right? So the Euclidean topology. Right. So the same will happen for this space here, in the sense that with this metric that we defined, the space G mod gamma is locally isometric to G. Okay, so, and let me state it more precisely. So proposition for all x in, so small x, okay, this is small x. For all x in G mod gamma, there is a radius R positive such that the map Px from the ball in G around the identity of radius R to the ball in X around X of radius R that sends G to gamma X. Oh, sorry. Let me write it like this. So X is in G. So for all gamma X in G mod gamma, this map here is an isometry. So is okay. So this tells you that if you pick any point in your set G mod gamma in your quotient, there is a small disk around that point, and it will, how small will depend on the point itself, such that the ball around that point of radius R is the same as the ball around the identity in G. Okay? And the proof of this is, well, essentially very easy. So let me write it here. Okay, good. So, idea of proof. So, suppose, okay, so you start with your point gamma x and fix a radius r positive, okay, and fix also g1 and g2 in the ball of radius r around the identity in G. Okay? Then you have the following. So you have the distance dx of gamma x g1, gamma x g2 is by definition, so by what I wrote there, the inf for gamma in gamma of the distance dg of g1 x to the minus 1 yes, gamma x g2. Okay? Good. So definitely you have that this distance gamma x g1 and gamma x g2 is less or equal than the distance between g1 and g2, because you have an inf here and you can just pick gamma equal to the identity. Okay, so then you have this inequality. So we want to show, to show the inf is obtained at gamma equals e. Okay, if you show that the inf is obtained at the identity, then clearly you have that here there is an equality. Okay, And okay, this is quite easy because so you have right. So you start from here. So pick a gamma in gamma such that this distance here, dg g1 x to the minus 1 gamma x g2 is less than the distance between g1 and g2, which is less than 2r, because g1 and g2 lie in the ball of radius r. Okay? Then this means, since I know that this g1 is at a distance at most r from the identity, this means that also dg from the identity x to the minus 1 x g2 is less than 3r, okay, by the triangle inequality. Okay, so x to the minus 1 gamma x g2, here I have g1, but g1 is close to the identity, is at most r from the identity. So, sorry, I can put the identity here and put the 3r here, right? And now I take this on the other side, and I have x gamma to the minus 1 x to the minus 1 g2. So these are equal, okay? And because the metric is left invariant, so I can just take this, the inverse of this, and put it on the other side. But now I know that g2 is at a distance at most r from the identity, right? And so this implies that the distance x gamma minus 1 x to the minus 1 identity is less than 4r. Okay? Good. But now, so the set, you notice that the set x gamma x to the minus 1 is discrete. So if r is sufficiently small, gamma to the minus 1 has to be the identity. Okay? So r small implies gamma equals the identity. Okay, and this shows that you have an isometry. Good. Okay, so then we have a metric. Yes?
A question just to make. So, the subgroup gamma, do you allow or do you not allow to contain rotations by rational angles?
Rotations by rational angles.
So your definition of discrete group?
No, it's any discrete group. Any discrete group.
Well, in a way one can include it in discrete in which sense. So, I saw that some people want to include it into the definition of some group.
No. For now, this definition is just discrete in this metric here that we have, this dg. Okay, so any discrete subgroup for now. But now I will make this definition a bit stronger. I will also ask for it to have a finite volume fundamental domain. Okay. Good. Okay. So this tells us that we actually have a metric, a good way of measuring distances on this space, on this portion. So the next step is to give this space a volume. Okay? So now we move on to 2. So we need a measure. So we need a measure on G mod gamma, and not just any measure, right? Because on G we have a dynamics, right? So the dynamics is right multiplication by by something, but by a matrix in G, right? And to do ergodic theory, well, you want that your flow, I'm not sure if this is correct in English, but preserve the measure. Right? So the measure that we have to construct here has to be a good measure to come so to go down to the quotient, but it also has to be invariant by right multiplication, right? So once it's invariant by right multiplication, we can do ergodic theorem, right? Okay, good. So how do we construct this measure? So okay, so remember, for us, G is PSL to R, which is also identical to T1H, right? Through the usual identification. So identification that sends G into G acting on II, okay? So first I want to construct a measure on G. And the way I construct a measure on G is the following. So I just take the hyperbolic, so I have a measure on H. So measure on H, which is just the hyperbolic area, 1 over y squared dx wedge dy. And I also have a measure on T1H, which is given by the volume form 1 over y squared dx wedge dy wedge d theta. So what is theta? Remember, the unit tangent bundle is just the hyperbolic plane. You have points, and around points you have circles. Okay, so circles of hyperbolic radius 1. So theta is just your parametrization of the angle coordinate here. Okay, so this is just a way of defining a measure of T1H on T1H. Okay, so good. Where am I? Right. And so, okay, if we want to have a chance of pushing this measure down to G mod gamma, we first need to show that this measure is invariant, at least left invariant. Okay, once we show that this measure is left invariant, then we can push it down to the quotient. Okay, so proposition. So both the measures so let me call this dA to be hyperbolic area, and this is the hyperbolic volume. So both the measures, say dA and dm, are left invariant. Okay, so how much time do I have? Okay, good. So all right, so just an idea of proof. So idea of proof. So suppose that you have a function f, a measurable function f going from h to r. Then you have to show that the integral over h of, say, f composite g and dA, where g is an element in your group, is also equal to the integral over h of f and dA. Right, so this is what you want to show. So to prove, so, but what is that, right? So you have the integral over h of f az plus b divided cz plus d, right? And then you have 1 over imaginary of z squared, which is also y squared, right? By the way we define our coordinates, dx dy, right? And you notice that the determinant of the absolute value of the determinant of the differential of g at a point z, so this is just a quick computation, is 1 over the modulus of cz plus d to the power 4. Okay? And not just this, but let's see, 4, 5. Okay, good. So you also have that the imaginary part of gz is equal, let me write it like this, g point z is equal to the imaginary part of z divided by cz plus d squared. Okay, so now you multiply and divide by this, and so this guy here becomes equal to what? F g, so g point z, and then so you have 1 over imaginary of z squared divided by cz plus d to the power 4 times 1 over cz plus d to the power 4 dx dy. And by a change of variables, this is just the integral over h of f w dw. Okay? So, analogous computation for dn. Okay? Good. So this shows that our measure, the hyperbolic area, is left invariant. And also the hyperbolic volume. You just need to do a little bit more computations. There's nothing complicated in this. Okay? Good. All right, so let's see. So now let me give you the following definition. So definition, a fundamental, so given, let's say, given gamma contained in G a discrete subgroup, a fundamental domain, so fundamental domain for gamma is a set E contained in G such that maybe let's call it F as fundamental domain, right? Such that the cardinality of F intersect gamma G is equal to 1. Okay, so this is just a subset. So subset, I see this now as a subset of G. Okay, meaning it's just a set that contains only one representative. Okay? Good. So what is our goal? Our goal is to, okay, we have the hyperbolic tangent bundle, so our goal is to identify some fundamental domain and use this fundamental domain to compute the measure, so to push down the measure to the quotient. Okay? So first of all, we have a measure on G, we have to identify a fundamental domain and use this fundamental domain to define a measure in the quotient. Okay? And good, so I'll start from the following fact. So the set E equals to Z in H such that the modulus of Z is larger than 1 and the real part of Z in absolute value is less than 1/2 is a, let me put it in quotation marks, is a fundamental domain for the action of gamma equals PSL2Z on H. Okay, so from now on, I will always assume that my gamma is PSL2Z. So instead of taking any discrete subgroup, I want to really specify what this discrete subgroup is, and tomorrow in the last lecture you will see why I'm taking this specific subgroup. So what's the connection to Diophantine approximation? Good, so let's look at this set. What does it look like? And I'll also tell you what a fundamental domain in quotation marks is. Okay, so this set looks like this. So here you have minus 1/2, 1/2, and here you have your semicircle of radius 1. Okay, so here you have a 0, this radius here is 1, and you're working with this set here. So this is your set E. Okay? So what do I mean by fundamental domain in quotation marks? I mean the following thing. So I mean that the hyperbolic area of gamma 1E intersect gamma 2E is equal to 0 for all gamma 1, gamma 2, and number 2, the union of gamma and gamma of gamma times E is equal to the hyperbolic plane. Okay, so what does this mean? This means that if I consider the action of this group on the hyperbolic plane and I take this tile, okay, I can act on this tile by using gamma, elements of gamma. I can cover the whole plane, this is condition 2, and condition 1 tells me that, okay, I can do it, and the intersection between two different tiles will have measure 0. Okay, so this is not a fundamental domain in the strict sense, because the tiles still have an intersection. Okay, but the intersection has measure 0. Also, it's not a fundamental domain in the sense that I defined here, right? Because here I'm talking about a fundamental domain F in G, and G is the tangent bundle. It's not H, okay? But still, if you consider the action of gamma on H, you can. This fact tells you that you can use this single tile to tile completely your space H by acting with elements of gamma. And we will use this fact to obtain a fundamental domain for the unit tangent bundle. So let me write it here. Okay. Good. Oh, and also I have a remark. So remark, the hyperbolic area of E is finite. And this you can compute, you can do by exercise. Okay? Good. So now we just notice the following thing. So let me use, do we have colors? So what was the right color?
Orange was the best one.
Yes.
And there's one on the table.
I'm not sure. Okay. So what happens is that if we eliminate this stripe here and this line here, then the tiles are actually disjoint. Okay? So let's call, so let E prime equal E minus orange. Orange parts. Okay, this is just, it's not too accurate. So define F to be the elements G in PSL2R such that G acting on I lies in E. Okay, so this is just a formal way of saying the following thing. So I take my fundamental domain on H, okay, and as a fundamental domain of the tangent bundle, so fundamental domain for the action of gamma on G, I just take points here in this set here and I stick to them arrows. Okay? So this will be my f, but instead of being just some surface, it's a surface with arrows pointing out. Okay, so this is my fundamental domain, f. And, okay, so exercise, show that f is a fundamental domain for gamma equals PSL2Z in G. By show, I mean formally. I essentially showed it for you, but okay, there's probably something still to check. Okay, and so, good. And now I'm ready to give the following definition. So definition, discrete subgroup gamma of G is a lattice. It's called a lattice if it admits a finite volume fundamental domain. And remark, the hyperbolic volume of the set F is finite. And this follows immediately from the fact that the hyperbolic area of E is finite. And this tells you that PSL2Z is a lattice. Okay? Good. So why did I work so much to define lattices? Because now I want to use a very powerful tool that tells me that whenever I have a lattice, I also have a measure on this quotient. Okay? And this is something Davide also used. So let me give you the following big fact.
I'm sorry, a question. So F is defined like G and I are on E or E prime.
Oh, good.
And what is the problem if you take E? What doesn't work?
So the tiles are not disjoint. Okay, so if you take, right, because you could have two G's here that, sorry, you could have, yeah, you could have two G's in this F if you put E that give you the same set, right? So remember, I got rid of this line, right? So you could take this point and translate it to, or let's say take this point and use the inversion. So Z goes to -1 over Z, and this point remains there. Okay? So essentially you have two elements that acting on I give you the same point, right? But, and also the same point in, so what happens is you have G1 and G2 in F such that G1 ZV, sorry, G1 II is equal to G2 II. Okay? But you don't want this.
Okay.
Wait, did I write it? Did I write it right? No, sorry. I think I made a mistake. So sorry. You have, I said something very stupid. Sorry. So you have that,
Maybe the easiest thing to see is that 1, 1, 0, 1 sends the left side, the left vertical strip to the right vertical.
Yeah, exactly. So that's what I wanted to say. So the matrix 1, 1, 0, 1 is a translation. So it sends this strip to this strip here, right? And this means that you have two representatives for the same element. Okay, so suppose that you pick an element G here, and you also pick, so this is your G1, this is your G2. If you use F as a fundamental domain, okay, so then the point G1 gamma has two representatives. Okay, so one is this and one is this. But you don't want this, because you want to have only one representative in this stripe. Okay? Does it make sense? Okay, good. Right. So now I want to use the following fact. I hope, yes, I have to have time. Good, so let me write it here. So fact, if gamma is a discrete subgroup of G and is a lattice, so is a lattice, then the measure, so again, for us, I don't want to go into deep into the theory, but for us, gamma is PSL2Z, okay, and G is PSL2R, okay. So then the measure M on G, or dm on G, is both left and right invariant. Left and right invariant, and therefore okay, maybe let's say, and also it can be pushed, it can be pushed down to G mod gamma by defining mx of B, where B is just any measurable set in G mod gamma equals x, okay, as the measure in G. Okay, so this is our hyperbolic area, so hyperbolic area as the measure of the intersection with the fundamental domain of the pre-image through the projection of the set B. Okay, so here you have some, if you want to see the picture, you have the quotient, okay, here you have your fundamental domain, you pick a set here, through the projection it will go into something here, and the measure of your set B is just the hyperbolic area of this set here. Does it make sense? Good. So the proof of this proposition is actually quite easy, but I don't want, yes?
Will you prove that you have a radius where your projection is an isometry? That's the way to build the fundamental domain in the general cases, to consider the distance of computations of a subgroup to the identity element?
I didn't hear the last part. Say again, sorry.
To consider gamma times small gamma times capital gamma times gamma minus 1.
Yes.
So distance that to the identity, it was the way that you find the R, which is the radius.
The injectivity radius, yes.
That's the way that you should that you proceed to find a fundamental domain when you have a more general lattice.
A more general, no. So this is the definition. So the definition is a lattice is a discrete subgroup that admits a fundamental domain of finite volume. Okay, so it doesn't mean that you always have a.
But let's say that I give you the subgroup. Now I'd like to know what is the fundamental domain. So I would like to rebuild it for the action of this subgroup on the hyperbolic space.
So given a different A different discrete subgroup, you mean?
Yes, a different discrete subgroup, and now I would like to know a fundamental domain for this subgroup in the hyperbolic plane.
Okay, so the way you describe this fundamental domain is completely by hand, it's not by using the metric. I don't know, probably there is also a way by using the metric, but I don't know. So this way here is really you have to take your group G and see that it's generated by translations and by the inversion, okay? And by using that, you essentially prove by hand that this is a fundamental domain. I don't use any metric fact here. Probably more generally you can do it, but I don't know, okay? Good. All right, so now we have a metric defined like this, and we can push it down to we've pushed it down to the quotient, and I want to highlight the fact that this metric is orange. Okay. I highlight the fact that this metric is also right invariant, okay? So the proof of this proposition is it's easy, okay? It's not too difficult. You just have to use the fact that the fundamental domain has finite volume. But I don't want to go into this now because I don't have time, right? So, and finally, so the last thing that I want to state is what I've promised you, okay? So this Dani correspondence, which is it's hanging from the very beginning. Okay, so let's erase this. So let's see. So now we have on x equals g mod gamma, we have a distance. So distance dx. We have a measure, mx, okay, which is right invariant, so invariant under right multiplication. And what we're left is free, we need a flow, okay? And the flow is very easy, so you have in T1H, you have the geodesic flow. So GTZV is just defined as G AT I. Okay, so through the identification, the geodesic flow is right multiplication by the matrix AT, where AT is e to the t halves, e to the minus t halves. Right? So and now push down, so the flow GT gamma G defined as gamma G AT is the quote-unquote geodesic flow on G mod gamma. Okay? So, and okay, I wrote quote-unquote because I always forget this. Okay, I wrote quote-unquote because it's the geodesic flow. A geodesic flow means that this should be, you should be able to see this as the tangent bundle of some surface. And the candidate surface is H mod gamma. Okay, so, but in reality there is some, I never remember what the problem is, but there is a small problem. So it's not completely true that G mod gamma is the unit tangent bundle of H mod gamma. So this is not quite the geodesic flow of this surface here, but still it is a flow in its own right. Okay, so now we have everything, all the ingredients that we need to state our correspondence. Okay. So let me state it here. Can I have 2 more minutes? Well, I think we started late. Thank you. Okay, so for ZV in T1H, define the visual map the visual map omega zv as the limit of the geodesic flow applied to zv. Okay, so you start from a point with a direction, this will correspond to a geodesic, and you follow it to the end. Okay, so omega goes from T1h to r. Okay, so let me write our quotient here. So this is our quotient, and let me state the theorem. So theorem, Dani correspondence. So GT ZV is contained, okay, let's say it's bounded. It's bounded in G mod gamma, or on the other hand, I also want to consider divergent orbits. Divergent if and only if omega ZV inverse, remember this is a real number, okay, is badly approximable or singular. Okay, so what does this mean? It means the following. So start from a point here. This is your ZV, okay? So what do? You follow it to the end. This gives you a point X here, okay? And the Diophantine properties of the point 1 over X are linked to what this orbit does here. What does this orbit do? Well, it follows geodesics, but then it's confined to stay here, okay? So it might do this, then it reappears here, and it goes down, then it reappears here, it goes down, and then it appears here, and so on and so on. So it will follow some trajectory, and so what's the only way to stay bounded here, okay? You can see this by how we defined the metric. Okay, I didn't really define what the metric dg is, but the metric dg is more or less comparable to the hyperbolic metric, okay? It's comparable to the hyperbolic metric, I didn't say this, but the only way you can go to infinity with the hyperbolic metric if you stay inside this thing is to go up here. So this correspondence says that if your orbit starting from here remains in this bounded set, then what you see here is badly approximable, or rather the inverse. Okay? On the other hand, if you have an orbit starting here that is divergent, so divergent means that I give you a compact set, then there is a time such that after that time you never return to that compact set. Okay? So this is divergent, then this point that you see here is singular. Okay? So this is the correspondence, next time proof. Sorry, I took 2 minutes more.
Are there any questions?
Yes.
In this definition of the area on the quotient, to define it, you really need to have the fundamental domain of a finite area, because you just can define it. The total area would be infinite.
So okay, I need a fundamental domain of finite volume because I want my measure to be left and right invariant.
Oh, so it would be a right invariant because of this, or
so but equally yeah. So if you have an invariant metric on G, I think you can prove. If you have an invariant metric on G, I think you can prove that. No, I'm sorry. I said so. If the volume of the fundamental domain is finite, this allows you to prove that all fundamental domains have the same volume.
Yeah.
Okay, so if this is not true, it's not a given that all fundamental domains have the same volume, right? So how do you push down the measure?
well, locally, but maybe.
Right, so this, yes, this really allows, and the fact that all fundamental domains have the same volume then it allows you to say that the group G is unimodular. Okay? But, so, yeah. But really I think it's, I think it's needed.
Okay. Are there any more questions? If not, let's thank the speaker again. And the next talk will be at 2012.
I'm a bit confused.